Chapter 1: Lenses. Now this is probably the last chapter in which we shall discuss optics. Very so often, many students get mixed up between the behavior of light on curved mirror surfaces and on lenses. But the simplest way to think about it is that mirrors reflect light, but lenses refract light. Let me take you through that before we discuss lenses in details. This is a plane mirror and this is a beam of light coming. And you see that as the beam comes in, it leaves at the same angle it came in all the time. But mirrors can also be curved. This mirror is concave, so as I come in parallel to the axis of the mirror, I leave always sort of aiming at a certain point. You see this point that seems not to change? That is the focal point of the mirror. There you go. All the parallel rays converge there. That defines the focus of the mirror. So a concave mirror is a converging mirror because it causes the rays from wherever they start to converge at that single point. But if I get the convex side, I got a diverging mirror. You see, it causes the rays to go up and down, up again and down. So that's a diverging mirror because it's convex. We have also discussed the principles of refraction. So as I send rays of light in here, if I send it straight, you see it enters the block and comes out and everything is fine. But if I send it at an angle, it's bending. Let me put the block like this. You see, I can get the ray of light to come in at an angle here. It changes direction and comes out. Notice this light coming in is parallel to the final ray that leaves, but in the medium it has a different direction. So notice in refraction, light actually passes through the prism. But in mirrors, it is reflected and bounces back. In this chapter, what we are going to see is refraction and not reflection. Light suffers refraction in lenses. It passes through, and the principle of lenses is simply derived from prisms. Let's see that now. We arrange two prisms so that their rectangular surfaces face each other. The parallel rays incident on the prisms emerge on the other side after refraction and intersect at a point. We insert a few more blocks of rectangular prisms between the first two. A parallel beam incident on such an assembly will undergo maximum refraction at its top and bottom. The rays undergo no refraction at the center of the lens. Now, if we arrange two more prisms to the side of this arrangement, then the incident ray emerging from them also converge at the same point. A single piece of glass formed in this fashion is called a convex lens. We can consider this equally curved surface of the lens to be small parts of spheres. The center of these spheres is called the center of curvature of the lens. The radius of the sphere is known as the radius of curvature of the lens. A line joining the center of curvature on both sides of the lens is called the principal axis, which passes through the optical center of the lens. The rays parallel to the principal axis and incident on one side of the lens undergo refraction and converge at a point on the principal axis on the other side. This point is called the focal point or the focus of the lens. The distance from the optical center to the focal point is called the focal length of the lens. The focal length of the lens depends on its curvature. If we have two lenses of the same diameter but of different thicknesses and hence curvature, when parallel light rays are incident on them, you can observe that the rays passing through the thick lens undergo more refraction and get converged at a shorter distance. as compared to the thin lens, which suffer less diffraction. So we see that the thick lens has a shorter focal length than the thin lens. The image formed by a convex lens in this case is a real image of an object. The convex lens can focus the light from the sun to a point on the other side of the lens. The concentration of light energy at this point causes the paper to heat up and burn. The lens in a human eye is convex in nature. You should not look at the sun directly, as it can damage our eyes permanently. So we understand that light rays incident on a convex lens converge at a point on the other side. So it can be called a converging lens. Let us now see what happens when parallel beams incident on the lens are inclined to the principal axis. After refraction through the convex lens, they converge at certain points on a plane containing the focal point. The plane passing all such points perpendicular to the principal axis is called the focal plane of the lens. What if the incident rays parallel to the principal axis are incident to the lens from the other side? This lens has the same effect on light incident from either side. Therefore, a convex lens has two focal points, usually represented as f1 and f2, one on each side, equidistant from the optical center. According to the principle of reversibility of light, a ray of light passing through the focal point of the convex lens emerges on the other side of the lens parallel to the principal axis. Let us now see another kind of lens which diverges light rays passing through it: concave lens. Place two prisms with their vertices in contact and arrange a few more pieces of rectangular prisms beside each of them. The parallel rays falling on such an arrangement refract away from the center. Overall, we can see that the light undergoes divergence and emerges on the other side. A single piece of glass formed in this fashion, having an inward curvature, is called a concave lens. Parallel rays incident on a concave lens undergo divergence as they emerge on the other side. If the divergent rays are extended backwards, they appear to meet at one point on the principal axis on the same side as the object. This is the focal point of the concave lens. The sun, viewed from a concave lens, would appear as a point. If you place a paper at this point, it will not be heated. The image formed in this case is a virtual image. A concave lens is used to correct eye defects called myopia. A concave lens is also used in peepholes of doors to get a minimized image of the person on the other side of the door. So in summary, an optical glass sphere can be cut in a required manner to obtain convex lenses. There are three types of convex lenses: the concavo-convex, the double-convex, and the plano-convex. Convex lenses are thicker in the center and become thinner at the edges. Rays of light incident to a convex lens converge at one point after refraction. That is why a convex lens is also called a converging lens. Similarly, a spherical glass sphere can be cut in a required manner to obtain a concave lens. There are three types of concave lenses: the convexo-concave, the double-concave, and the plano-concave. Concave lenses are thinner at the center and thicker at the edges. Rays of light through a concave lens appear to diverge from a point. So concave lenses are also called diverging lenses. Let us now turn and look at image formation by lenses. Now, when light from an object falls on a lens, an image of the object is formed. However, unlike in mirrors, image formation in lenses is the result of refraction of light and not reflection. The nature of image formed depends on the type of lens and the distance of the object from the lens. Ray diagrams are usually used to locate images formed by lenses. It is important to note that when constructing ray diagrams, 1. Real rays and real images are drawn in full lines. Virtual rays and virtual images are drawn in broken lines. After drawing the image, you need to describe it. Now, here are the characteristics to look for. 1. Nature of the image. Is it real or is it virtual? 2. Orientation. Is it upright? Is it inverted? 3. Relative size to the object. Is it magnified? Is it diminished? 4. Position on the principal axis. Is it at F, between O and F, between F and C, or at infinity, and on which side relative to the object? Ray diagrams. Convex lens. Now, we've said ray diagrams are used to show the formation of images by lenses. Now, when locating the image, generally 2 of the 3 rays shown here are considered. 1. A ray passing through the optical center of the lens travels straight without suffering any deviation. 2. An incident ray parallel to the principal axis after refraction passes through the focus. And 3. An incident ray through the focus emerges parallel to the principal axis after refraction. Concave lens. First ray. A ray of light parallel to the principal axis of a concave lens after refraction appear to diverge from its focus. Second ray. An incident ray through the optical center of the lens is undeviated. Characteristics of images formed by lenses. Convex or converging lenses. To construct a ray diagram, we need at least 2 rays whose paths after refraction from the lens we know. The image is formed at the point where these lines intersect. The rays are chosen according to our convenience. First is an object positioned between F and O. So we choose any 2 rays among the 3, whichever is applicable. First, a ray parallel to the principal axis after refraction passes through the focus, F. Then, a ray through the optical center passes through undeviated. Now, these refracted rays appear to intersect only when extended backwards. Therefore, for an object placed between F and O, a virtual, erect, and magnified image is formed behind the object. Next is an object positioned at C. We start. A ray parallel to the principal axis after refraction passes through F. Next, A ray through the optical center is undeviated. The two rays are sufficient, but we can still test with the third one. That is, a ray through F after refraction emerges parallel to the principal axis. The three rays meet at C. Thus, when an object is placed at C of a convex lens, a real inverted image of the same size is formed at C on the other side of the lens. Next is an object positioned between F and C. First is a ray of light parallel to the principal axis after refraction passes through F. Next is a ray through the optical center which proceeds undeviated. The two rays are sufficient to locate the image, but you can still confirm with the third one. That is an incident ray through F which emerges parallel to the principal axis. The three rays intersect one another at a point beyond C. Thus, when an object is placed between F and C of a convex lens, a real inverted and magnified image is formed beyond C on the other side of the lens. An object positioned at F. We proceed normally. A ray parallel to the principal axis passes through F after refraction. Next, a ray through the optical center proceeds undeviated. Now these two rays are parallel to each other and will never meet. Thus, for an object placed at F of a convex lens, a real inverted and magnified image is formed at infinity. An object positioned beyond C. First ray, a ray parallel to the principal axis passes through F after refraction. Second ray, a ray through the optical center proceeds undeviated. Next, an incident ray through F emerges parallel to the principal axis. Now the refracted rays meet at a point between F and C. Thus, for an object placed beyond C of a convex lens, a real inverted and diminished image is formed between F and C on the other side of the lens. Object at infinity. Now, the rays of light coming from an object at infinity are always parallel to each other. Now, case 1, when the incident rays coming from an object fall obliquely on the lens. Now, an incident ray through the focus of a lens emerges parallel to the principal axis after refraction. Next, an incident ray through the optical center is undeviated. The two rays meet at F. Thus, for an object at infinity, a real inverted and highly diminished image is formed at F. Case 2, when the rays of light coming from the object are parallel to the principal axis. The rays of light parallel to the principal axis after refraction converge at the focal point. Thus, for an object at infinity, a real inverted and highly diminished image is formed at F. Concave lenses. Now, again, to construct a ray diagram to allow us to locate the image, we need at least two rays whose paths after refraction we know. Where the refracted rays meet, there is the image. Now, for concave lenses, there are three case scenarios that we look at. First, an object at infinity. First ray, rays parallel to the principal axis after refraction diverge, appearing to originate from F. Therefore, for an object at infinity, a virtual erect and diminished image is formed at F. Next is an object between O and F. First ray, a ray parallel to the principal axis after refraction emerges diverged seemingly from F. Next, a ray through the optical center passes through undeviated. Thus, for an object between O and F, a virtual erect and highly diminished image is formed between O and F. Finally, an object beyond C. An incident ray parallel to the principal axis is diverged seemingly from F. Next, an incident ray through O is undeviated. Therefore, for an object placed beyond C, a virtual erect and diminished image is formed between O and F. Next, we look at linear magnification. Now, linear magnification M is defined as the ratio of the height of image to the height of the object. Magnification M is equal to height of image over height of object. Now, consider an object OB placed in front of a convex lens. OB is the height of the object and IM is the height of the image. Let U be the object distance PO and V the image distance PI. Triangles POB and PIM are similar. Therefore, IM over OB is equal to PI over PO. Therefore, image height over object height is equal to image distance over object distance. Magnification M therefore can also be represented as image distance over object distance. M is equal to V over U. Then we look at the lens formula. Consider an image formed by a converging lens as shown on your screen. Now in the figure, PO is the object distance U, PI is the image distance V, and PF is the focal length F. Distance OB is equal to PH. Triangles POB and PIM are similar. Therefore, OB over IM is equal to PO over PI, which is equal to U over V. Similarly, triangles PFH and IFM are similar, and so PH over IM is equal to PF over IF. But then PF is equal to F, the focal length. IF is equal to PI minus PF, which is equal to V minus F. Substituting these values in equation 2, OB over IM is equal to F over V minus F. Combining equations 1 and 3, U over V is equal to F over V minus F. UV minus UF is equal to VF. UV is equal to VF plus UF. And UV is equal to, factorizing the right hand side, F into V plus U. Dividing both sides by F, UV over F is equal to V plus U. And therefore 1 over F is equal to V plus U over V, which is equal to V over UV plus U over UV. 1 over F is therefore equal to 1 over U plus 1 over V. This equation is known as the length formula and holds for both converging and diverging lenses. Note, however, that when numerical values of F, U, and V are substituted in the formula, their appropriate signs must be included. The sign convention of real is positive is adopted. Take an example. An object is placed 15 centimeters in front of a convex lens of focal length 10 centimeters. Calculate the image distance and the magnification. Now in the solution, 1 over F is equal to 1 over U plus 1 over V, that is the length formula. Therefore 1 over 10 is equal to 1 over 15 plus 1 over V. 1 over V is equal to 1 over 10 minus 1 over 15, which is equal to 1 over 30, and therefore V is equal to 30 centimeters. Now, determination of the focal length of a converging lens. Now, different methods are used in the determination of the focal lengths of lenses. Now, the following experiments will illustrate some of these methods. Method 1. Focusing a distant object. Now, we have seen that the image of an object at infinity is formed at the focal point. Simple. So locate some distant object like a tree from the window of your lab. Place a meter rule in the direction of the object. Now place a convex lens mounted on a stand vertically along the meter scale such that the midpoint of its base is at the 5 centimeters mark. Place a white screen behind the lens such that the base of the lens stand and the screen remain in line with the meter scale. Move the scale back and forth until a sharp inverted and diminished image of the distant object is formed on the screen. Now the distance between the lens and the screen is the focal length of the lens. You can adjust the positions of the convex lens and the white screen to obtain several values of focal length and calculate the average focal length. Method 2, using the lines formula. Is 1 over f is equal to 1 over v plus 1 over u, subject to sign changes depending on the case at hand. Now arrange a candle, a screen, and a convex lens as shown here. Adjust the position of the lens so that a blurred image of the candle is obtained on the screen. Now move the screen back and forth until a sharp image is formed on the screen. Measure and record the distance between the lens and the object, and also the distance between the screen and the lens. Repeat the experiment by changing the positions of the lens and then the screen until a sharp, well-defined image of the candle is formed on the screen. The focal length can be determined using the lens formula. Power of lens. The power of lens is property of its focal length and is a measure of its refracting ability. The power of a lens is given by power is equal to 1 over focal length in meters. The unit of power is diopters, D. A lens of short focal length refracts light more than that of large focal length. Thus, a lens of short focal length is more powerful than that of a larger focal length. Converging lenses have a positive power, while diverging lenses have negative. For example, the power of a converging lens of focal length 10 centimeters is given by power is equal to 1 over 0.1, which gives us plus 10 diopters, or simply 10D. That of diverging lens of the same focal length is given by 1 over negative 0.1, which is equal to minus 10 diopters. Applications of lenses. Simple microscope. A microscope is a device that is used to view very small objects that cannot be seen distinctly with the naked eye. A simple microscope uses the principle of a magnifying lens or reading glasses. A simple microscope consists of a convex lens of short focal length mounted on a plastic or metal holder. When an object is placed between the principal focus and the optical center of a convex lens, a virtual erect and magnified image is formed. This ray diagram shows how an object is enlarged when viewed through a biconvex lens. Observe that the object and the image are on the same side of the lens. Image is formed at the least distance of distinct vision from the eye. That is, the distance from the object is approximately equal to 25 centimeters. Compound microscope. There are two cases under which converging lenses can produce magnifying images, namely, when the object is between f and 2f, and when the object is between lens and f. A compound microscope combines the two. It consists of two converging lenses of short focal length. The lens next to the object is known as the objective lens, and the one next to the eye is known as the eyepiece or ocular. The objective lens is of short focal length. The eyepiece is also of short focal length but longer than that of the objective lens. The object to be viewed is placed between f0 and 2f0 of the objective lens so that a real inverted and magnified image is formed. This image is in front of the eyepiece and acts as an object to it. The eyepiece is adjusted so that the image falls between its principal focus f0 and itself. This way, the eyepiece acts as a magnifying glass and produces a final image that is greatly magnified. A compound microscope overcomes the limitation of a simple microscope by use of an objective lens with many lenses and eyepiece with more than one lens. A natural application of the lenses is the human eye. The human eye is a natural optical instrument. The eye is designed to focus light into specialized nerve endings that translate light waves and photons into pictures our brain can understand. The eye is located close to the brain so that its messages can be relayed quickly. The eyeball is completely surrounded by a layer of soft, fatty tissues and placed within a bony socket for protection. From the inside of the socket, this is how the eyeball looks like. The white stalk is called the optic nerve, which connects the eye to the brain, and also these muscles which move the eyeball. The capsule of the eyeball has 3 layers. This thick, tough outer layer is called the sclera and protects the delicate structures within. This transparent, bulging portion is called the cornea. There is also a crystalline lens, which is one of the main parts of the human eye. The second layer is called the choroid. It consists of 3 different zones. The first zone is called the choroid proper and is the part that carries nourishment to the tissues of the eye. The next zone is called the ciliary body. This is the thin, broad, ring-shaped band of thin muscle fiber which plays an active and vital role in the visual adjustment of the eye. The third zone is the iris, which expands and contracts the pupil, much like the diaphragm of a camera. The innermost layer is the retina, a very delicate membrane. The retina is actually the part of the optic nerve which transmits light impulses to the brain. The retina is the most important and complex structure of the eyeball. It consists of complicated arrangements of rods and cones which convert light waves into nerve impulses. Between the lens and the cornea is the aqueous humor, consisting mostly of water and a little salt. This larger space within the eye is filled with vitreous humor, consisting chiefly of water mixed with salt and albumin. It is a highly transparent jelly-like substance and plays a very important role in visual adjustment. The reflected light of the world enters through the crystal transparency of the cornea, pupil, aqueous humor, lens and the vitreous humor, and then project onto the photoreceptors of the retina. The macula is a very small area at the center of the retina that gives us a fine pinpoint center of vision. The area of retina surrounding the macula gives us a peripheral or side vision. The retina converts light waves into signals that are sent to the optic nerve and then to the brain. Continuous adjustment of the pupil and the lens regulates the entry and focus of light. Defects of vision. Myopia. Myopia is an eye defect due to which an eye is unable to see distant objects clearly. This occurs when light rays entering the eye converge in front of the retina in the vitreous humor. Here you can see the image formation in a normal eye and a myopic eye. In the case of the normal eye, light rays from the flower fall on the eye and converge on the retina. Whereas in the myopic eye, the rays are focused in front of the retina. Myopia occurs due to elongation of the eyeball, that is, the distance between the retina and the eye lenses is increased, or decrease in the focal length of the eye lens. A concave lens is used to correct this optic abnormality. The ray diagram shows how the concave lens helps focus light on the retina. Hypermetropia or hyperopia. This is an eye defect in which distant vision is clear while near vision is blurred. This occurs when light rays from an object converge behind the retina. Here you can see the formation of an image in a normal eye and in a hypermetropic eye. In the normal eye, light rays from the flower fall on the eye and converge on the retina. Whereas in the hypermetropic eye, the rays from the flower converge behind the retina. Hypermetropia is caused by shortening of the eyeball, that is, the eyeball becoming smaller, or increase in the focal length of the eye lens. A convex lens is used to correct this abnormality. The ray diagram shows how a convex lens helps to focus light rays onto the retina. Presbyopia. The term presbyopia means old eye, and a person suffering from this condition loses their ability to focus on close objects. That is, presbyopia is a variant of farsightedness or hypermetropia. It is a natural process of the aging eye. It is not a disease and cannot be prevented. Symptoms are normally noticeable around 40 to 45 years of age. Some signs of presbyopia include the tendency to hold reading materials at arm length, blurred vision at normal reading distance, and eye fatigue, along with a headache. Bifocal lenses are used to correct this defect. Astigmatism. Astigmatism is the most common eye problem, resulting in distorted images as light rays are prevented from meeting at a common focus. Astigmatism may accompany hyperopia or myopia. Normally, the cornea is conical in shape, but in an astigmatic eye, the cornea is shaped more like a rugby ball. The shape causes light rays to focus on 2 points rather than on just 1 point. You can see here how the graph paper appears to a normal eye and an astigmatic eye. An astigmatic eye cannot simultaneously focus all objects or lines. That is, an astigmatic eye may only see the vertical lines or the horizontal lines on a graph paper. This can be corrected by using cylindrical lenses. Now, before winding up, some 2 important things to remember all the time regarding mirrors and lenses. First, mirrors reflect light. That is to say, light rays hit a mirror surface and bounce back. But lenses refract light. That is to say, light rays pass through lenses but bend or change direction when they do that. Second thing, and this is very important, concave mirrors converge the rays after reflection, but concave lenses diverge the rays after refraction. The exact opposite. Then, convex mirrors diverge rays after reflection, but convex lenses converge rays after refraction. I hope you remember that from now. Good luck.
You can make a bigger difference in the world. You can make a positive change in your career. You can make a greater contribution to the greater good. And you can start today by earning your degree online at Walden University, where advanced degrees advance the quality of life.